So we've seen the benefit of having an orthonormal basis. Now we got to figure out, how do we take a basis and turn it into an orthonormal basis? And we can actually use that idea of projections. So if you remember back a few sections, we talked about the projection theorem. And we said that we could take a vector and project it onto another vector and then find a decomposition where one vector is parallel and one vector is orthogonal to the vectors. So we said we could decompose this vector into two pieces, where v1 is going to be parallel to vector w and v2 is going to be orthogonal. And v1 can be found by taking the dot product of v dot w over the magnitude of w squared. And we said that we could generalize this to any inner product by writing it this way, where this produces a scalar value. So v1 is always going to be parallel to w since it's a scalar multiple of w. v2 is the orthogonal piece. It will always be orthogonal to w. So Gram-Schmidt kind of takes that idea, and instead of doing it with maybe just two vectors, what if we have a basis in R3? Then we could expand this to three vectors and make all three orthogonal to each other. Or we could expand to four vectors if we're in R4, or five if we're in R5, and so on. And we can do it under any inner product, not just a dot product. So it's really an extension of that projection theorem that you started talking about back in the trig class where you were first introduced to vectors. So let's look at this. We're going to say B is a set of basis vectors in some vector space V that's formed by an inner product. So B prime they're using as the orthogonal basis here. So there's our notation understanding. So the way this works, we're going to let W1, our first basis vector in this orthogonal set, just be V1. So W2 is going to be orthogonal to W1, and to find that, we're going to take V2 minus the inner product of V2 with that first vector here over the inner product of W1 with W1, which is that first vector. That's going to form a scalar value, and we're going to multiply it by W1. It's the exact same thing we did here when we found that vector. So same kind of concepts being applied there. Now, if we needed to move this to three vectors, then we're going to build that third vector off of V3, which is from that original set of vectors that's not orthogonal. And then we're going to use some inner products pairing V3 with W1 and W2. And then so on and so forth. So once we go through this process, we're forming an orthogonal basis. Well, an orthogonal basis is nice, but we need an orthonormal basis usually. So to find an orthonormal basis, we're really just going to take those basis vectors that we just found that are orthogonal, and we're going to normalize them, which means we're going to set them up so that they all have a magnitude of 1. So let's try this guy out. Let's look at this example. We have three vectors. They're telling us it forms a basis for R3. I'm not going to prove that, but if you wanted to, you could go through and you could prove that it forms a basis for R3. So let's form that orthonormal basis. So we're going to start by applying Gram-Schmidt. So W1 is always going to be equal to V1. So V1 is the vector 1, 1, 0. And I'm going to use that parentheses notation again instead of the vector notation that we're used to since we're talking about vectors with inner products. I don't want to mix those two up. And to be consistent with the textbook here. To find W2, our formula is V2 minus the inner product of V2 and W1 over W1 with W1. And then we're going to multiply that scalar value by W1. So I'm going to compute some of those inner products over here to the right. Now, they haven't given us a specific inner product, which means we're always going to assume it's the Euclidean inner product, which is the dot product. If they wanted something else, they would have to tell us what it is. So let's find V2 and W1. So V2 with W1 would be 1 times 1, which is 1, plus 2 times 1, plus 0 times 0. And then we need W1 with W1. So 1 times 1 is 1. Plus 1 times 1 is 1, plus 0 times 0 is 0. So we have V2 minus the dot product of V2 W1, which is 3. The dot product of W1 with W1, which is 2, times W1. So we have 1, 2, 0 minus, and I'm going to go ahead and distribute this through 3 halves, and 0. So our W2 vector, our second vector, is negative 1/2, 1/2, and 0. So now we need to look at W3. The formula is V3 minus dot product of V3 W1 over W1 W1. That's a scalar value multiplied by W1 minus V3 W2 over W2 W2 times W2. So we need to find a few things. We need to find V3 and W1. So V3 and W1. So we're going to have 0 plus 1 plus 0, which is 1. We need to find W2 dotted with itself. So negative 1/2 times negative 1/2 is 1/4. 1/2 times 1/2 is 1/4. Plus 0, that's going to give me a half. And then we need to find V3 W2. So V3 W2 would be 0 plus 1/2 plus 0, which is 1/2. So there's all my dot products I had to find. Substitute in what we know. V3 is the vector 0, 1, 2. The dot product of V3 and W1 is 1. W1 is 2 times W1 minus the dot product of V3 and W2 is 1/2 over W2, which is 1/2 times W2, which is negative 1/2, 1/2, and 0. So we have 0, 1, 2 minus 1/2, 1/2, 0 minus negative 1/2, 1/2, 0. So we're going to have 0, 1 minus 1/2 is 0. 2 minus 0 is 2. So there's our W2. So our bases here, W1 is equal to 1, 1, 0. W2 is equal to negative 1/2, 1/2, 0. And W3 is equal to 0, 0, 2. Oops. So if we were to form dot products with W1, W2, and W3, every combination would give us 0. This is guaranteed to be an orthogonal basis. But now we want to take it a step further and find that orthonormal basis. So let's do that on the next page. So I'm going to call it U1, U2, and U3. So U1 is going to be 1 over the magnitude of W1 times W1. So the magnitude of W1 would be square root of 2. So U1 would be 1 over square root of 2, 1 over square root of 2, 0. U2, we're going to normalize it. So it's going to be negative 1/2 squared plus 1/2 squared plus 0 squared. So this is 1 over the square root of 2/4 times W, which is 1 over the square root of 2 over 2. So that's 2 over square root of 2 times W. This is W2. So W2 was the vector negative 1/2, 1/2, and 0. So our U2 vector negative 1 over square root of 2, 1 over square root of 2, and 0. And then U3, 1 over the magnitude of W3 times W3. The magnitude of W3 is 0 squared plus 0 squared plus 2 squared. So that's going to be 1/2 of W3. So there's our U3. So then our orthonormal basis consists of these three vectors. So what's interesting about Gram-Schmidt's orthonormalization process is that we can apply it with any definition of an inner product for any basis set. So it doesn't have to span all of R3. It can just span something like a plane in R3. So let's look at example 8. We have two vectors. It spans a plane in R3. So we only have to have two vectors here to do that. And we want to find an orthonormal basis for this subspace. So we already have a basis, but we want one that's orthonormal. So the process is going to be the same. W1 is going to be equal to V1, which is our first basis vector. W2 is V2 minus the inner product of V2 with W1 over the inner product of W1 with W1. And we're going to dot that with W1. So let's compute a few things, and I like to do that off to the side. Inner product of V2 with W1. So if I dot this with this, I'm going to get 0 plus 1 plus 0, which is 1. And then if I dot W1 with itself, I'm going to get 0 plus 1 plus 0, which is also 1. So there's some side work. So our basis vector, our second one, will be V2 minus the dot product of V2 and W1 over the dot product of W1 and W1 times vector W1. So I get 1, 0, 1. So here are my two basis vectors. These are orthogonal to each other, and it's really easy to see that if we were to find the dot product. But now we need to normalize it. So U1, we 1 over the magnitude of W1 times W1. So the magnitude of W1 would be that, which will just give us a 1. So we're going to get 0, 1, 0. So U1 ends up being the same vector, since it already had a length of 1. And let's find U2. And there she is. That one has a length of 1 also. So now U1 and U2 form an orthonormal basis that spans the same space as this guy. So let's look at one where we're not using the standard Euclidean inner product. Suppose we have a basis, 1x and x squared in P2. So notice that's the standard basis. And we're applying a different inner product. This inner product is based on integration. And we want to find an orthonormal basis. So the process is still the same. The only difference is our definition for our inner product. So W1 is still V1, which is still going to be our first factor, and I'm going to call that X. I'm calling these V1, V2, V3, just to identify those. W2 is V2 minus the inner product of V2 and W1 over the inner product of W1 with W1. Then we're going to multiply by W1. So we're going to do some scratch work off to the side. The inner product of V2 and W1. We're going to integrate from -1 to 1. And we're going to apply this definition. So it's going to be Px, which is our V2, times our Q, which is 1. It's coming from that W, times dx. So if we integrate x, we get x squared over 2, going from -1 to 1. So we're going to have 1/2 minus 1/2, which is 0. And then we also need to find W1 with W1. W1 is 1. So if I integrate 1 times 1 dx, integrating 1 gives us x, going from -1 to 1. And we're going to get 2. So this piece becomes V2 minus V2 W1 over W1 W1 times W1. So we're just going to get x for that. So now we need to find W3. So that is V3 minus V3 W1's inner product over the inner product of W1 with itself times W1 minus V3 with W2 over the inner product of W2 with itself times W2. So let's compute a few things off to the side. We need V3 with W1. V3 is x squared, W1 is 1. When we integrate, we get x cubed. If I plug a 1 in, I get 1/3. If I plug -1 in, I get -1/3. So we're going to get 2/3 for that inner product. We need to find V3 with W2. V3 is x squared. W2 was x. So we're integrating x cubed, which is x to the 4th over 4. Going from -1 to 1. So we're going to have 1/4 minus 1/4, which is 0. And then we need W2 with itself. W2 was x, so x times x. That's x squared. When I integrate x squared, I get x cubed. So here are my inner products I had to find. So let's plug everything in. So we have V3 minus the inner product of V3 W1, that's 2/3. Inner product of W1 with W1 was 2 times W1, which was 1, minus V3 W2 was 0. So that's going to be nice. W2 is x. So this is going to reduce to x squared minus 1/2. Just kidding, minus 1/3. 2/3 divided by 2 is going to give you 1/3. So there's our orthogonal set. If we were to apply the inner product to W1, W2, they will be orthogonal. W1, W3 will be orthogonal, and W2, W3 would be orthogonal under this definition of inner product. Now we need to turn this into an orthonormal basis by normalizing. So to find U1, it's going to be 1 over the magnitude of W1 times W1. So we've got to find the magnitude of W1. So if you remember the definition of that, it is the square root of the inner product of W1 with itself. So let's find the inner product there. W1 with W1. Actually, we already found that. That was up here. And that was 2. So this guy ends up being the square root of 2. So we have 1 over the square root of 2 times W1. So our U1 vector is 1 over square root of 2. So to find U2, it's 1 over the magnitude of W2 times W2. So let's find that magnitude of W2. The definition is the square root of the inner product of W2 with itself. And we already found this guy up here. And we got 2/3. So we have 1 over the square root of 2/3 times W2. And W2 was x. So that's the same thing as the square root of 3/2 times x. So then U3 is 1 over the magnitude of W3 times W3. So to find the magnitude of W3, that one we haven't found yet. That is the square root of W3 with W3. And remember, we're under this definition of an inner product. We're defining it by integration between -1 and 1. So let's find W3 with W3. So we're integrating from -1 to 1, x squared minus 1/3 times x squared minus 1/3 dx. So that's x to the 4th minus 2/3 x squared plus 1/9. When I integrate, I get x to the 5th over 5 minus 2/3 x cubed over 3. And when I divide by 3, that's going to change that to a 9. Plus 1/9 x. Integrate from -1 to 1. If I plug in 1, then plug in the negative 1. So that gives me 2 over 5. So that's minus 1 over 9, minus 3 over 9, minus 2 over 9. Which is going to give me 8 over 45. So the magnitude of W3 would be the square root of 8 over 45. So all this is side work. So now let's plug everything into this formula. So we have 1 divided by that times W3 so that's going to be equal to the square root of 45 over 8 times x squared minus 1/3. We can break down the square root of 45. That's 9 times 5, which is 3 square root of 5. 8 is the same thing as 2 square root of 2 times x squared minus 1/3. So there's our final answer. If we wanted to, we could distribute that 3 through and rewrite that slightly. Square root of 5 over 2 square root of 2 times 3x squared minus 1. Either one would be perfectly fine. So there's our U3. So our orthonormal basis would be these 3 vectors. So as you can see, the Gram-Schmidt process is definitely an involved process. Sometimes it's easier to go through the normalization process before you find the vectors, the second vector and the third vector and so on. So there's an alternative form of the Gram-Schmidt process which does that. So let's look at that. So normally with Gram-Schmidt, let me go back to so you can see and I can point to things. Normally with Gram-Schmidt, your first vector is your first vector. In the alternative form, we're taking that first vector and we're going to go ahead and normalize it. So this guy is already a normal vector, which means it has a length of 1. And then we use that to help us find this next vector. And then we go ahead and we normalize it. See how that U1 that's normalized is included in that formula here. Okay, which is essentially the same formula that we had back here. Only now we've got a normal vector here and here. So we may have some square roots that we have to deal with. And then we normalize that vector. And then we would use that U2 here to compute our W3. And then we normalize W3 and so on. Sometimes it makes it easier. Sometimes it's more complicated. In all honesty, I like to use Gram-Schmidt as is and then normalize later. But I think there's definitely value in showing you this alternative method. So let's look at one. Example 10. We want to find an orthonormal basis for the solution space of the homogeneous linear system. So in other words, we're finding the null space. And the null space is going to be the solution space for that homogeneous system by definition. So let's take this guy, let's pop it into the calculator. Let's do RREF. So if we do RREF on that, here's what I got. So I know x1 is equal to negative 2x3 plus x4. I know x2 is equal to 2x3 minus 8x4. And I know x3 and x4 are free. So the null space, which is the solution space for this homogeneous system, is going to look like this. It's going to have two vectors in it. Coefficients of x3 are that. Coefficients of x4 are that. So there's our V1 and our V2, and we've defined those. So that's the basis for the solution space of the homogeneous system. In other words, that's the basis for the null space. Now let's go through and let's find an orthonormal basis for this space. And we're going to use that alternative form. So our U1 is going to be our V1 divided by our W1. Excuse me, our V1 divided by the magnitude of V1. Now, notice we do not have any inner product defined here, so we're assuming that it's the standard normal Euclidean inner product, which is going to be our dot product. So the magnitude of V1, so we have negative 2 squared plus 2 squared plus 1 squared plus 0 squared. So that's square root of 9, which is 3. Times V1. So we're going to have 1/3 times V1. And I'm going to write the vectors this way, horizontally instead of vertically. So we have negative 2/3, 2/3, 1/3, and 0. Now, this guy is already a normal vector because we went ahead and we normalized it in this step. Put parentheses around that and make that a little bit easier to see that that's a scalar value. So it's already normalized, so we won't have to do that at the end. It's kind of takes out two birds with one stone, so to speak. So to find W2, going back to the alternative form, W2 is going to be V2 minus that dot product of V2 and U1 multiplied by U1. So we have V2, which is 1 negative 801 minus, and we need to find this guy, V2U1. So we have 1 times negative 2/3, negative 8 times negative 2/3, 0 times 1/3, 1 times 0. So negative 2/3 minus 16/3 is negative 18/3. And that is equal to negative 6. So we have a minus. This is negative 6 times u1. So 1, negative 801 minus negative. I'm going to go ahead and change that to a plus. And then I'm going to distribute that 6 through. So it's negative 12 over 3, which is a negative 4. over 3, which is a negative 4. 6 over 3, which is 2, and then 0. So we're going to have minus 3. Let me check my signs real fast. So I changed this to a positive here. So positive 6 times 2/3 would be a positive 4. Positive 6 times 1/3 would be a positive 2. And then 0. So what's your signs on these? So we get negative 3, negative 4, 2, and 1. So this is W2, but it's not normalized. Now we have to normalize it. So 1 over the square root. Negative 3 squared is 9. Negative 4 squared is 16. 2 squared is 4. 1 squared is 1. Times W2. So that's square root of 30 times W2. So then our U2 is negative 3 over square root of 30. Negative 4 over square root of 30. 2 over square root of 30. And 1 over square root of 30. So there's our final answer. And we found that using that alternative form here, where we first found V1 and then normalized and then found W2 by plugging in the U1s and then normalized, and then we would keep going if we needed more vectors. Like I said, I prefer doing all my normalization at the very end. I think it's just easier, especially if I have something with square roots in it. I prefer using this method over the alternative.